Hi everyone, welcome to my YouTube channel. My name is Steven Taiwo, and in this video we'll be going through my assignment on statistical machine learning together. Basically, I carried out two machine learning tasks, one of regression and the other one of classification. So let's get into it. For the first exercise, I carried out some data exploration to look out at what the input space and the output space of my data look like. And I discovered that the output space is a subset of real number, thereby it's continuous, and which make it a regression task. The input space has 225 observations with just one dimension. So I plotted the scatter plot of y against x to see the relationship between y and x, and I could see a nonlinear relationship. And this led me to deciding on the function space to use. I decided to use the polynomial function space of degree at most p. This is because of the nonlinearity between y and x. So the L2 loss function was used for our regression task, which is because it's advantageous because of its convexity property. It it's helped to minimizes well, which is essential in obtaining the best machine. The theoretical risk is defined. We also have the Bayes learning machine, which is the universal best machine, and the expression for the empirical risk is also given here. So moving on to estimating the best model for our data. To do this is just by finding the OLS estimator, the ordinary least square estimator. This is just finding the machine that minimizes the empirical risk, and this boils down to finding the coefficient of the polynomial that minimizes the expression for the empirical risk. This leads us to solving this differential this by differentiating the empirical risk and equating to zero, leading us to solving the normal equation. So the OLS estimator has some property, which is that it is unbiased and it's also a random variable. So the optimal complexity is just the degree of the polynomial that balances the trade-off between bias and variance. And to do this, we employ the method of B-fold cross-validation. This simply means we are splitting our data into B-fold and leaving one out, training it on the other, and coming back to test it on it and calculating the cross validation error. This is repeated on all degrees, and the average cross validation error is calculated. The one that minimizes the cross validation error is picked as our optimal complexity. And when I did this, I discovered that the degree of 10 is the optimal complexity of for my model. And I fitted three models: the complex, the optimal, simplex, and I could see that the optimal model really fitted my data where it generalizes whereby if new data is introduced, it will be able to predict it well. But the simplest, they only captured the data but didn't do a lot of things. So moving on to getting the test error distribution for this model, and this confirmed that the optimal model is really the best model. The complex model has large variance, a bit slightly larger than the optimal model, and the simplest model is the worst model here. The ANOVA test also confirmed that the optimal model, there's a statistically significant difference between the three models. After performing a pairwise comparison, we discovered that the optimal model is still performing better. So moving on to the second task, which is a classification task, just as I mentioned earlier. Looking into the data, discover that the output space is a categorical variable having just two classes. So I can say that this task is a binary classification. Is a binary classification task. It has just two classes, spam or not spam. It's just to decide whether an email is a spam or not. So looking at the input space, we have 4,001 observations and the dimension is 57. This confirms that we have enough data to build our model. So we try to fit four different models on our data: LDA, QDA, naive Bayes, and the FLD. Although the LDA and FLD are the same thing because we are dealing with the binary classification, and looking at the ROC curve, we see that the naive Bayes is the worst model here, but the LDA and QDA are doing and performing better, although LDA come out fine. But after performing a stratified holdout to to test and train our data, we discover after getting the test error, we have that the LD and FLD are doing better. Thank you.